Welcome to Crystal Clear Chemistry channel. In order to crack either JEE means or NEET exam, let's strengthen our basics through this channel. And in this video, I am going to discuss about the structural isomerism, the basics of the structural isomerism in detail. I have already uploaded some of the basic concepts of organic chemistry as a part 1. Go through the checklist. Not only the basics, I am going to upload the grand tests papers of either JEE means or NEET exam. So please go through the playlist. You can see some of the grand tests already that I have solved. Okay. Without any delay, let's get into the topic now. Structural isomerism. First of all, what is isomerism? Existence of compounds with the same molecular formula but different properties, nothing but isomerism. Suppose if we consider these two compounds CH3O CH3 and C2H5OH, they are having the same molecular formula C2H6O, but they are differ in their properties. They are the ethers, and if you consider this C2H5OH, it is an alcohol. They differ in their properties, but they are having the same molecular formula. The type of phenomena is nothing but isomerism, and such compounds are called isomers. Such compounds are called isomers. Example 1, suppose if we consider these two compounds, both are having the same molecular formula C2H6O, but their properties are different. They have different structures altogether, right? Now if we consider C4H10, total of C carbon 4 carbons are there, and there are 10 hydrogens. If we consider this particular compound also, there are 4 carbons and 10 hydrogens. So C4H10 is the molecular formula of this particular compound. So we can write with the same molecular formula, but different different structural formulae, and which are having the similar molecular formula or similar general formula, we can say, but they differ in their properties, and hence such compounds are called isomers. Let us see how many isomers are there. Isomerism is of mainly two types: structural isomerism and stereoisomerism. Structural isomerism in the sense having the same molecular formula, but different structural formula, nothing but structural isomerism. If we consider the stereoisomerism, in the case of stereoisomerism, both the molecular formula and the structural formula both are same for a particular compound. But if we consider the groups or the atoms, their spatial arrangement is different. Spatial arrangement of groups are different in the case of stereoisomerism. Okay. Now in this video we are mainly focusing on this particular structural isomerism, where the compounds are having the same molecular formula but different structural formula. Structural formula is mainly of 5 types: chain isomerism, position isomerism, functional isomerism, metamerism, and tautomerism. For example, if we consider the structural isomerism, compounds having the different properties, it is due to the difference in their basic structure. That's what. If the compounds, for example, if we consider these two compounds, they differ in their structures, and hence they differ in their properties, and these two are called structural isomers, and the phenomena is structural isomerism. Okay. Now we came to know that the chain isomerism is of structural isomerism is of 5 types: chain, position, functional, and metamerism and tautomerism. So let's discuss one by one in detail. First one, chain isomerism. The difference is the size of the chain. Where we have the difference here, in the size of the chain we have difference with the same number of locates. That means, suppose if we consider this particular compound CH3, CH2, 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 CH3, this is called N-pentane, right? In the long chain there are 5 carbon atoms. But if we consider this particular compound, there are only 4 carbon atoms, and there, there is, sorry, 4 carbon atoms in the long chain. This is called isopentane, we know. And we have neopentane also, where the main chain, while writing the IUPAC name, the main chain contains 3 carbon atoms, but all are having the same molecular formula. That means they differ in the size of the chain. This is 5 carbon chain, the same formula, 3 carbon chain, 4 carbon chain, and hence all the three are called chain isomers with the formula C5H12. You can count the number of hydrogens here, it's C5H12. Okay, with the same number of locates. With the same number of locates in the sense, total of 5 number of carbon atoms are 5, right? So here also there are 5 carbon atoms, so differ in their size of the chain. Okay. Now, position isomerism, compounds with the same molecular formula but locands or substituents or uh, occupy the multiple bonds. Okay, or multiple bonds if we consider substituents, multiple bonds or functional groups if we consider, if their positions are different on the same carbon main chain, then we can call them as the position isomers. Once again, position isomers means compounds with the same molecular formula. As the name indicates, they differ in the position of substituents or multiple bonds or the functional groups or whatever it may be. Okay. Now see here, if we consider the orthonitrophenol, this OH and NO2, this is called orthonitrophenol, and this is called metanitrophenol. They differ greatly in their boiling points, and the group's positions are different, right? So we can take this as a positional isomer. These two are positional isomers. And a few more examples for the positional isomerism. If we consider this particular example, this is having 5 carbons and this is also having 5 carbons. That's what the main chain size is same. Main chain size is same in the case of position isomerism, but the position, if we consider the multiple substituent like CH3, the position of CH3 is different. In the first case it is 3 methyl pentane, in the second case it is 2 methyl pentane. Now, functional isomerism. What is functional isomerism? Compounds having the same molecular formula but with the different functional groups are called functional isomers. Functional isomers. For example, if we consider alcohols and ethers, aldehydes and ketones, carboxylic acids, esters, primary, secondary, tertiary amines, nitriles and isonitriles. What are all these pairs of compounds means? For example, if we consider the first example, CH3, CH2, CH2OH, it is having the formula C3H, this is 8, C3H8O, and if we consider this particular compound, it is also having C3H8O molecular formula. In the first structure, OH is the functional group. In the second structure, O is the functional group. So in the first structure, alcohol, first compound is alcohol, second compound is an ether, but both are having the same molecular formula. That's what they have paired up. Alcohols and ethers are can be the functional isomers with the same number of carbon atoms, aldehydes and ketones, carboxylic acids, esters, primary, secondary, tertiary amines, nitriles and isonitriles. You can clearly see this second example also. This is CHO, this is CO, aldehyde ketone, having the same formula but different functional groups. Acid COOH, ester COOR. Check the particular carbon atoms, 3 carbon atoms, and hydrogens are 6, oxygens are 2. So both are having the same molecular formula but different functional groups, hence these two are functional isomers. Then what about that primary, secondary and tertiary amines? If only one NH2 is there, then it is called primary amine. If NH is there, it is called secondary amine. If only N is there, then it is called tertiary amine. In fact, all the three are different group of atoms and they are different functional groups. And hence we can say that all the three with the same molecular formula are said to be the functional isomers here. Check the carbon atoms also. Here there are 3 carbon atoms and the remaining also contains the same number of carbon atoms, but if we consider their functional groups, they are different, hence functional isomers. What about the last one? This is nitrile, right? CN. This is isonitrile. Okay, cyan. They have did not mention. See, this is wrong actually. You have to write it as NC. So this is cyanide and this is isocyanide, cyanides and isocyanides. That's what they are saying, that nitriles and isonitriles are the functional groups with the same number of carbon atoms. Okay. Now this is all about the third isomerism. What about the fourth isomerism? It is nothing but metamerism, right? Phenomena of molecules having different number of carbon atoms on the either side of the functional group. If we take a functional group like oxygen, on the either side of the functional group, if having different number of carbon atoms, different number of carbon atoms, then it is said to be metamerism. If we consider CH3, CH2O, CH2, CH5, on the either side of this functional group, number of carbon atoms are different. This 2 and 2. Here if we consider this one, this is 1 and 3. So they greatly differ by their number of carbon atom on the either side of the functional group. Then that type of isomers are said to be metamers. What and all can be the metamers? Suppose if we consider this particular first example, ethers. Ethers can be the metamers with the same number of carbon atoms, right? Same number in the sense, if there are 4 number of carbon atoms, if there are 4, on the either of the 1 and 3 we can write, or you can write 2 and 2, right? So that's what they have done here. These two together called metamers. Similarly, along with the ethers, there are esters, ketones, and the secondary amines which can exhibit the metamerism. Okay. Now, what are the conditions for exhibiting the metamerism? Functional group should be polyvalent or at least heteroaromatic. Polyvalent, heteroaromatic, and the nature of the functional group should not change. Both are ethers. Functional group should not change. And if we consider the nature of alkyl groups, chain and position isomerism is not considered. If they differ in their chain or position isomerism, we should not consider. And the nature of the two alkyl groups and the position of the functional groups should be different. So nature of the alkyl group is different in the sense, if we consider uh, the previous example here, here there are 2 carbon atoms and here there are 2 carbon atoms, but here if we consider 1 and 3, both are having the same formula but differ in their alkyl groups, right? So nature of two alkyl groups and position of the functional group should be different. These are the conditions for the metamerism. Okay. Now listen here. The last isomerism is all about the tautomerism. For the mains exam, the tautomerism topic is very important as it is not included in the NCERT textbook. For the NEET students, it's not that important, but tautomerism is very important for JEE main students. Okay, now, now listen here. Uh, it is the phenomena in which a molecule exists in two rapidly interconvertible structures by the shift of one hydrogen atom. Just by the shift of one hydrogen atom, there exist two structures and which are interconvertible rapidly. The obtained two forms are called tautomers and they are also called dynamic isomers. Let us see what they are. Types of isomerism. There are four different types of isomerisms: ketoenol tautomerism, nitro acynitro tautomerism, imine and enamine tautomerism, nitroso and isonitroso tautomerism. Compounds must contain at least one ring electron withdrawing group like NO2 or CHO. What are the conditions for tautomerism? Compound should contain at least one ring electron withdrawing group like NO2 and CHO, etc. And the compound should contain at least one alpha hydrogen. Let us see what is alpha hydrogen and all, which is present on the adjacent carbon of the functional group. If any functional group is there, the adjacent carbon of the functional group is called alpha carbon, and that alpha carbon should contain hydrogens, at least one hydrogen, to exhibit the tautomerism. Let us see through an example here. Suppose if we consider, one minute, yes. Suppose if we consider this particular example, this is an electron withdrawing group C double bond O. So for this C double bond O functional group, these two are said to be alpha carbons, and whatever the hydrogens that are attached to them are called alpha hydrogens, right? So if we consider the hydrogens count here, there are total of 6 alpha hydrogens in the case of acetone. In the case of acetone. Now, just because of the shifting of one of the hydrogen from this carbon to the oxygen, double bond becomes single bond and single bond becomes double bond, and this particular compound is called, this particular form of the compound is called enol. Why it is called enol means there is a double bond and double bond present in the compound, and hence it is ene. Ol means OH, so there it is an enol form, and this is the keto form. Keto means C double bond group is called keto group. So among keto group and the enol form, if we consider, there exists equilibrium, dynamic equilibrium. Both are interconvertible from one another, and that phenomena is nothing but the tautomerism. Here the keto form is more stable when compared to the enol form. Okay, now you can clearly check here the H plus ion, why it is, how it is shifting from H3O plus means actually it is from the solvent. There is OH plus, and then because of this plus ion, the bond will shift here so that you will get so that the positive charge can be neutralized. But if you consider this particular carbon, it gets the positive charge. So there is a hydride shift from the adjacent alpha carbon, and hence we got this particular form. Okay, we got this particular form, and this is nothing but see here you need to write it as CH double bond C O H. Whenever H plus is removed, you can also see the structure here. Let's take another example. So for example, if you consider this particular CH3 C double bond O CH3, base catalyzed mechanism also you can check here. Okay, now stability of ketoenol forms. Uh, as there are two types of tautomers, uh, as there are two forms in the tautomerism, one is keto form, the other is the enol form. We need to check which is more stable. Stability of the keto form is more than the enol form due to the higher C double bond O energy than the C double bond C bond energy. So the bond between C double bond O is higher when compared to C double bond C, and hence keto form is more stable. Okay, in the form of assertion and reason type questions, you can come across this particular point. Once again, among keto form and enol form, as C double bond O bond energy is higher than that of the C double bond C, keto form is more stable. Okay, so like this, as we are discussing many basics in through my channel, please don't forget to subscribe to my channel. If you really like the video, if it is really helpful for you, please share to your friends. Okay, now anyhow, continue the topic here. The stability of end for the stability of end from in a dicarbonyl compound can be explained on the basis of resonance. Dicarbonyl compounds, in the case of dicarbonyl compounds, let us see which is more stable and why. There are mainly two reasons. They are nothing but the resonance and the intramolecular hydrogen bond. See, for example, if we consider this particular compound, yeah, 1 minute. So can you write the enol form for this, and which is more stable? Which is more stable means the C double bond O as linked to the aromatic compound, as there is a conjugation, A is more stable. Effect of solvent. Keto form predominates enol form in the presence of polar protic solvents like water, alcohol, acetic acid, NH3, etc. This is because the oxygen atom of the keto group enters into intermolecular hydrogen bond with that of the solvent. So if there are polar protic solvents, keto form is more stable because keto group forms a hydrogen bond, intermolecular hydrogen bond. Whereas in the case of enol form, in the case of non-polar solvents like benzene, hexane, enol form is more stable as there exists a intramolecular hydrogen bond. Okay, this suppose if we consider this particular example, arrange the following in the decreasing order of their enol content. If we consider this particular PHCO, CH2CO, CH3, as whenever there are two carbon atoms, carbonyl compounds are there, there exists intramolecular hydrogen bond, and hence enol form is more stable. That's the reason why it is more stable due to intramolecular hydrogen bond. And if we consider the remaining compounds apart from this, uh, here also there is a C double bond or two C O's are there, but here one extra factor is conjugation, and here you can see only the intramolecular hydrogen bond. Here also you can see the intramolecular hydrogen bond, but not the conjugation. Here, because why there is a conjugation in D, as there is a pH. Okay. Now acenitrotautomerism. In nitro compounds like N double bond OO containing at least one alpha hydrogen, shift of that hydrogen yields two interconvertible forms. One is nitro form and the other is acenitro form. See, for example, shifting of this alpha hydrogen here and here double bond. That's what this is acenitro form. So apart from keto-enol tautomerism, there is a nitro-S-nitro tautomerism also. Okay. Now the next one, imine-enamine tautomerism. Imine is nothing but double bond between CH and NH. Enamine tautomerism nothing but amine means NH2, ene means double bond, ene and imine. Because of the transfer of hydrogen from here to here, there is a double bond transfer from enamine to imine, and this is also a tautomerism as they are interconvertible from one another. And another tautomerism, nitroso and isonitroso tautomerism, you can clearly see here. Whenever there is a N double bond over there, that is called nitroso form, and whenever there is a isonitroso group, that is nothing but NOH nitroso form. Okay. Now, alkyl nitroso compound having alpha hydrogen. This is nitroso compound. This is a functional group. This is the alpha hydrogen. It contains a alpha hydrogen, and this shifting to the oxygen. That's the reason why they are interconvertible by the transfer of alpha hydrogen, and hence this type of tautomerism is said to be nitroso isonitroso tautomerism. So what is the previous one? Imine enamine tautomerism, and then nitro nitro tautomerism, and we know already about the keto enol tautomerism. And this is very important. In the case of keto-enol tautomerism, dicarbonyl compounds, the stability is the enol form is more stable. It is because of the resonance and the intramolecular hydrogen bond. Okay, I'll quote one example in the form of a short after this video. Okay, thanks for watching the video. Please subscribe to my channel. Thanks for watching.